Welcome students. We want to discuss about arc length and curvature. So suppose you're given a curve r of t. So this curve is given by r of t. And suppose this point is r of a. These are the position vectors. So r of t is the position vector of these points on the curve. And this is r of t. And you want to find out what is the length of this curve. So the way it works is you basically find out small lengths like that and then add them using Riemann sum. Yeah. So the idea would be you have, so these small lengths can be approximated by the length of the tangent. So it's going to be r prime, r. So this small thing can be approximated by r of ti prime delta t, length of this, and then you take the summation I going from 1 to n, and then you take limit and then goes to infinity to refine this thing. And this is what gives you the length of the plane curve C. So the length of plane curve C is given by integral a to b absolute value of r of t prime of t dt. And if your r of t is in two, it's a vector function of vector valued function g of t, then r prime t is going to be f prime t g prime t, and when you take the absolute value of this, you get square root of f prime t square plus g prime t square. And then when you sub it here, you get your length of arc. So similar thing can be done for a vector equation, vector valued function, which gives a curve. So suppose the curve C is defined by equation R of t, which has three components, f of t, g of t, h of t, where t ranges from a to b, and we want that f prime, g prime, h prime are continuous. We want nice functions. And if the curve is transversed exactly 1 as t increases from a to b, then the length of the curve is given by a to b, f prime square plus g prime square plus h prime square, the whole square root dt. Yeah, this is same as, if you look at it, if your r of t is ft gt ht, now your function has three components because you're in the space. So r prime is going to be, r prime t is going to be f prime t g prime t h prime t, and when you take length of this, you get square root of f prime t whole square plus g prime t the whole square plus h prime t the whole square. And then when you substitute, you find r prime t dt, you compute this, you get this integral. Yeah. And the same thing can be written if your x is equal to f of t, then dx by dt is going to be f prime t. Yeah, so substituting that, we get this formulation as well. So now we have an expression on how to find out the length of the curve. So let's do this problem here. Find the length of the arc of the circular helix with the vector equation r of t equals to cos t I plus sine tj plus tk. So first of all, note that it's a circular helix. So the way circular helix looks like is the following. You have cos t. So if you think about it, this is like x squared plus, if you have this as x, if this is your x and this is your y, you have x squared plus y squared equals to 1. So it's like a circle, but this t is kind of unraveling the circle up. So we have, so this is your x-axis, this is your y-axis, and this is the z-axis. Then we start with 0, 1, 0, 0. Then you're going in this direction like a circle, but you're unraveling it up. It's going up like that. Yeah, as t keeps increasing. So however, we need to find out the length of the arc. So length of the arc is L. Now where's my t changing from? So t is changing from, so let's see, how can we get t from here? So we see that the third variable or the z variable indicates t. So you see that t is changing from 0 to 2 pi, right? So we have L is 0 to 2 pi r prime of t, absolute value of that dt. So this is going to be, so before we compute that, let's compute r prime of t. So r prime of t is, derivative of cos t is minus sine t, derivative of sine t is cosine t, and derivative of t is 1. So this implies r prime length of this is going to be square root of sine square minus sine t square plus cos t square plus 1. So sine square t plus cos square t is 1. So this is 1. So we get the whole thing is equal to 1 square plus 1, so 2, so square root of 2. Therefore, length is going to be 0 to 2 pi square root of 2 dt, which is square root of 2 times t, 0 to 2 pi, which is going to be 2 pi times square root of 2. So this is the length of the arc. Okay. Now, from this length of the arc, we can get what is called as arc length function with a small modification. The beauty of this function is that it captures, it gives a parametrization for you. So let's see how. So suppose C is a piecewise smooth curve given by vector function R of t is f of t I plus g of t j plus h of t k, where your t is between a and b. And the curve C is transversed exactly once as t increases from a to b. Then the arc length function is given by s of t is a to t r prime t dt. So what does it really captures? If you think about it, your starting point corresponds to, this is r of a. So s of t, this is a scalar function, right? What does it capture? So if your t corresponds to, so if you're, for t, you're here, then this length along this thing, this part is your s of t. Yeah, so this scalar length gives you your s of t. Now, why is this an interesting function too? Why is this an interesting function to have? Because it kind of depends on the intrinsic nature of your curve. All right, it doesn't depend on what coordinate system you have. It depends on, so you see s of t basically just goes along the curve to find out, yeah, to get the arc length function. So if you apply the fundamental theorem of calculus, you have ds by dt is going to be, you substitute t inside here, right? So it's going to be r prime of t. So this is from the fundamental theorem of calculus. And so we'll see how reparametrization. So we're going to reparametrize the r of t, which is given by this with respect to arc length function. So we're going to use arc length to parameterize the the helix. All right, so the idea is the following. So let's first compute the s of t. So s of t is, first of all, s of t is equal to 0 to t, because you're starting from t equals to 0, 0 to t, r prime of u. So it's going to be r prime of u. We don't want to use the same variable as there. So absolute value of r prime of u du. But we have already computed what is r prime. So r prime is square root of 2. So we have from the previous example dt, which is root 2 t. So therefore, what do we get? Therefore, this implies t equals to s by root 2t. And the reparameterization of your helix is then r prime r of s, which is also r of t of s, right? Because we are replacing t with s. T is also function of s, right? From here, this is going to be cos of s square root of I plus sine square root of s by square root of 2j plus square root of s by square root of t k. Now this is reparameterization of the same curve. So you will basically go along the same curve, but here the parameterization is in terms of the arc length. Okay, so it's more natural of a parameterization. So next topic we want to discuss is about the curvature. So the idea is we say, oh, the road is too curved, right? When you're driving, yeah. And sometimes the road is not curved at all, right? It's almost straight. Okay? So we want to formalize these ideas. So what does it mean by curvature? Yeah. So we want to capture the intuitive idea of, oh, the road is too curved. So the idea is the following. The curvature of a curve is the magnitude of the change of unit tangent vector with respect to arc length. So what is the change of unit tangent vector? So we have ds by, so we can write the tangent vector as ds. So let's just, so you can write, this is your tangent vector. You take derivative of that with respect to s, and then you basically take the magnitude of that, and that gives you the curvature. Why is that? See, if you take look at this one here versus this one. So this one has bigger curvature, bigger curvature. Why is that? Because it is curving quite fast, right? The curve is bigger. Here it takes a bigger turn to get to here. So this one has bigger curvature. And if you think about the tangent basically, the tangent line changed from here to here, it's already in the opposite one. Whereas here, compared to the arc length, it takes a long time to, or relatively longer time than the first one to turn back. Okay. So the idea is, this is what we capture by curvature. So let's have, so curvature is the, again, the magnitude of the change of unit vector, unit tangent vector with respect to arc length function. So we have ds by dt, d of t divided by ds. So now let's work on this problem. So find the curvature of the helix. So first of all, we have tangent t. So we need tangent t, which is nothing but t prime t divided by what? So t prime, so tangent is r prime, right? So first what we'll do is we will write r, so we need to find out the tangent. So first we'll find s of t. So steps are the following. First find s of t. So s of t is 0 to t r prime t, or r prime u, we'll not use the same variable there, r prime u du, which we have already found out to be root 2 of t. So step 2 will solve t in terms of s. That is, we get what? S by root 2 equals to t. Then step 3 will reparameterize. So we get r of t of s is going to be cos of, now cos of s by square root of 2 ti plus sine of s by square root of t j plus s by this k. Now we want to find out, so this is the r of t of s. So now this can be thought of as r of what? R of s, right? So generally we'll write this by, let's denote this by capital R of s. So then what do we need is we reparameterize this guy. So now what is r prime of s? So what do we get? We get tangent now, right? So to get tangent, we need to have r prime of s. That is going to be 1 by square root of 2 with a minus sign of sine of s by square root of t s. So we get this guy. What is derivative of this with respect to s is going to be cos of s by square root of 2, and then square root of that is going to be multiplied by 1 by root 2, and then that is going to be 1 by root 2. So now what is length of r prime? So we need to find out r prime s divided by r prime of s, this length. This will give me my t of s, the tangent. So this is C. I'm using capital R because I cannot use the same R here because this was in function of t. Now I'm writing it as a function of s. So this is going to be, so note that r prime s, so r prime s, if we look at this vector, the length is 1. So we get, this is going to be same as 1 by 2 square root of 2 s by cos of s by square root of 2 times 1 by 2, 1 by root 2. So this is your t of s. Now we have to, what? We have to take dt ds. So derivative of this with respect to s. And then we get, so note that the r prime s should not have been, I mean, like, since we are parameterizing based on the arc length, the r prime s will have to be 1 anyway. So let's compute now ds by dt and see what do we get for the for the so this is going to be minus 1 by 2, derivative of sine is cosine s. Now similarly we had 1 by root 2 here. Derivative of cosine is minus sine, so minus sine s by square root of 2 multiplied by 1 by root 2, and then we get derivative of this is going to be 0. So this is going to be db 1 minus 1/2 cos s by square root of 2 minus 1/2 of sine of s by 2 square root of 2 comma 0. And now if you take the length of this gives you a curvature kappa that is, so s is a scalar, so dt by ds, length of this is going to be length of this vector, which is going to be half cos of s by square root of t whole square plus half minus half sine of s by square root of t whole square plus 0 square. So this square half will come out and you get sine square theta plus cos square theta, which is 1. So the curvature is 1 by 2. So now instead of going through this reparameterization, we could have done in a slightly different way rather. So if C is a curve, piecewise smooth curve given by the vector function r of t, where t changes from a to b, then the curvature k at point P is given by r of t, which is kt, which is t prime divided by r prime t. Now, how do we do that? How do we look at that? We have k equals to dt by ds. So to compute this, we can do the following. Notice the following. So you have dt by ds is same as now your t is a function of your tangent vector is a function of s and s is a function of t. So you can write, in fact, you can write d by dt, dt by dt is equal to derivative of this tangent vector with respect to s multiplied by ds by dt. So if you divide that on the other side, you get ds divided by d. So this has to be dividing it on the other side. So I'm bringing this and dividing it on the other side. I get dt by dt divided by ds by dt. Now note that this is a scalar, so it's okay to divide. We are not dividing by a vector. So we have dt by ds. So absolute value of this is equal to absolute value of that. So this can be rewritten as, so this implies this can be rewritten as, the top can be written as t prime t and the bottom can be written as r prime t, right? So therefore you have another way of computing the curvature. Another way to compute the curvature is our curvature at t is r prime t times cross r double prime t if you take length of that and divide by r prime t cube. So here the key is you need to show that dt, so derivative of your tangent vector with respect to t is r prime t cross r double prime t divided by, so if you take length of this guy, it's going to be prime t squared. Okay, so these are the ways we can compute the curvature. So there are three methods to compute the curvature. One is to first, again, if you're given a helix or any parametric curve, you reparameterize it based on the arc length and then compute you write your tangent vector t as a function of your arc length, and then you basically go by definition. That is, you look at d by ds of vector tangent vector t. That means you're seeing how is the ds, which is what the magnitude of the unit vector. And when you take the derivative, you're looking at the change of unit vector with respect to arc length. Then the second one is basically we did use chain rule to simplify it. And then third one is we have another formulation of it. So let's look at the problem and use. So either one of this is going to be helpful to solve this problem. So let's try with essentially computing curvature. Now we can use either one of them. Let's use the first one. Sorry, let's use this definition. So we have r prime of t is going to be 3, 4 cos t, 4 sine t with a minus sign. Your r double prime of t is going to be 0, minus 4 sine t, minus 4 cos t. So then we are computing this quantity here to find out the curvature. So first compute r prime t cross r double prime of t. So we compute the cross product is going to be I j k 3 4 cos t minus 4 sine t, and then you have 0 minus 4 sine t minus 4 cos t. So let's compute this. So we have this is equal to, so I times, so 4 times 4, so it's going to be 4 square cos square t with a minus sign minus 4 sine square t minus j, so minus 12 cos t, then that will be 0, so minus 12 cos t. And then the next one would be plus k, I should use cap, k, so you ignore this one, so you get what? Minus, so we get minus 12 sine t. So therefore, we get prime t cross r double prime t, length of this is going to be, so first of all, first one can be simplified, right? You can take minus 4 out, you get sine square t plus cos square t, which is 1. So the first one is going to be simply 16 with the minus sign. Second one is going to be plus cos t, 12 cos t. And then the next one will be minus 12 sine t. And we already have, so we want to take length of this guy. So going to be length of this one here, which is going to be 16 square plus 12 square cos square t plus 12 square sine square t square root. And then the answer is 16 plus 12. So we can take So this will become 1. So it's going to be square root of 16 square plus 12 square. We can take 4 out. In bracket, we will get 4 square plus 3 square, which is 5. So we get 20. And what is r prime of t? And length of that is going to be square root of 3 square plus 4 cos t square. So 3 square. Sine square t plus cos square t is 1. So we get 3, we get 5. So therefore, we get the curvature kappa is going to be this 20 divided by 5 cube, which is 20 divided by 125. Now, another factor is, what about the plane curves? That means they are in the plane. How do we get the curvature of those curves? So consider the following plane curve y equals to f of x. And then we have the curvature is given by the following formula. How do we go about it? Well, we can compute this in the following way. Same formula here. So first we need to have r of x. So r of x is, we'll parameterize in terms of x instead of t. So, well, x coordinate is x, f of x, and then the y coordinate is what? 0. Now we need r prime x. R prime x is going to be 1 f prime x 0, and r double prime x is going to be 0 f double prime x 0. So what is r prime x cross with r double prime x first? So we'll compute this first. So I j k 1 f prime x 0, and here we'll have 0 f double prime x 0. So now in determinant, you expand using the top row, but you can also expand using the bottom. So it's going to be plus minus plus. So you can write this as f double prime x. Now you have to forget about this row, sorry, this column and this row. So you will have in bracket, you'll have I, again, this vector is vector I. You want to write a cap or an arrow, doesn't matter. They are well known what they are. So I 1 k 0, and this is going to be minus, so f double prime x times k with a minus sign. We already know what is r prime of x, and length of this, that is going to be square root of 1 square. So here, right, we have here, so 1 square, which is 1 f prime x, the whole square root. So therefore, k of x, the curvature is given by, so what is length of r prime cross r double prime? It's going to be length of this object here, and length of this object is simply f double prime of x with the absolute value, divided by length of r prime x, the whole power. So we have 1 plus, so length of this divided by what? 3 by 2, right? So we have basically power is what? The power is 3. So we need, so we have 1 plus f prime x, the whole square root to the power 3. And in that case, the curvature comes out to be this whole thing to the power 3. So The formula should be corrected. Square root of this to the power 3. So this is your curvature. So let's compute the curvature in this example. At what point is the curvature y equals to e to the x has maximum curvature? So let's see. So f prime x is e to the x. F double prime x is also e to the x. Curvature is given by the following formula. F double prime x e to the x absolute value divided by 1 plus f prime x, which is e to the x, the whole square, the whole power 3. Okay, so this is the curvature. So now note that denominator is always bigger than the what? Bigger than the, so denominator is always bigger than the numerator, right? Because you're squaring and then you have 1 plus e to the power 2x, so this is going to be bigger, right? So this is a curvature, and you can see that it's always going, the numerator is also positive all the time, so this is your 1 plus e to the power 2x, the whole power 3. So this is your curvature. Now, there are two questions asked here. One, does it has a maximum curvature? So again, that becomes a problem of calculus 1, how to find maximum value of this function. So for that, we need to find critical point. So take k prime x equals to 0. This implies e to the x plus 2 times e to the power 3x divided by 1 plus e to the power 2x to the power 5 by 2. You can do that calculation, equals to 0, which gives e to the x equals to 2 e to the power 3x, because the denominator cannot be 0, right? Exponentials are never negative. So we are only interested in the critical point, which arise out of equating 0 to 0. So we get, this gives us half equals to e to the power 2x, and therefore we get x equals to what? Minus 1 by 2, so ln of 1 by 2 of ln of 1 by 2. Yeah, so this is the point at which you will have a critical point, and then you can show using second derivative that that's going to be maximum, or you can also use the sign diagram to show that. Okay, so we have got the maximum curvature. Now what happens to the curvature as x goes to infinity? So as x goes to infinity, so 1 is done, 2. As x goes to infinity, what happens to this thing? As x goes to infinity, you can see that denominator will go to 0 faster and numerator will become, so the numerator is fixed, the denominator is getting faster. So we should work it out, limit as x goes to infinity, kx, so divide top and bottom by highest power of, so we have divide top and bottom by e to the x. So I'm going to divide by e to the power 2x by 3, sorry, 2 of, so look at the denominator. So denominator is roughly, so if you look at this part, so if you look at this part, it's going to be e to the power x, roughly the whole power 3. So I'm going to divide top and bottom by e to the power 3x. So this will become square root of 1 plus, so 1 by e to the x plus 1 by e to the power 2x by e to the power x. Now the whole cube. Yeah, so I'm dividing top and bottom by e to the power 3x. Now this becomes limit as x goes to infinity, e to the power minus 2x. The denominator simplifies to 1, e to the power minus x plus plus 1, the whole cube, and as x goes to infinity, this goes to 0. So the curvature becomes 0. So therefore, let's write this again. As x goes to infinity, the curvature goes to 0. Okay. So now we have some idea about the curvature of the curve. Let's move on to the next discussion about Frenet-Serret frame. So let's see a smooth curve, which is given by r of t, vector function, where t is between a and b. So we'll define two more vectors, unit vectors, normal, binormal. So you have, first of all, you have tangent already. And then you have unit tangent. You have normal is defined to be take the derivative of the tangent and divide by its length. And then binormal is the cross product of tangent, unit tangent vector times normal. So these three things form coordinate system for each point on R of t. So if you look at any point, say let's move here. At these points, there will be three mutually orthogonal or perpendicular vectors. It's like x, y, z, right? So, and they basically give you tangent, normal, and binormal. So the idea is if you have normal like that, you have a tangent vector in this format. So this is your tangent. Suppose this is your normal, this is your tangent. Then binormal is given by t cross n. Yeah, so it's basically given by the cross product. Okay, so it's basically these are the three vectors, and they basically give at every point they are giving a coordinate system. Okay. So now there are a few more interesting objects. Uh, so oscillating plane at point P is the plane which contains T and N. So if we have a plane containing T and N, so here, for example, you have T and N. So tangent is this red one. Normal is this other one here. Then the plane containing these guys is in some sense plane which is passing, is basically is touching the curve from the back here, right? So such a curve is called osculating plane. So, and it contains T and N. Now, similarly, we have an osculating circle. So if you look at any curve like that, at any point P, you look at the concave side. So there are two sides. Look at the concave side. The concave side is here. And then you draw the largest circle which will fit. This is the osculating circle. So for example, here at this point 0, this is the largest circle which can fit inside just touching at this point. So such a circle is called osculating circle. So the largest circle tangent to the curve that completely lies on one side of the curve is an oscillating circle. And what is the radius of it? If this is a curvature K, at this point, the curvature is Kx at this point, at 0, the curvature is kx, then the radius of this circle is 1 by k, or 1 by kappa, whatever we can call it. So the idea is now you can decide which one has bigger curvature, right? So here a smaller circle will fit, but here there's a much bigger circle which will fit. So in that sense, since the radius and the curvature has inverse relation, smaller the radius, bigger the curvature. You see there's a bigger curvature here. And it kind of makes sense from the definition too, that that this curve moved on quite quickly, whereas here, because of the bigger oscillating circle, has to the tangent move quite slowly along this. Okay. So let's see. So in this example, which point P or Q has a bigger curvature? So if you look here, the circle which will fit here at P, so let's look at the circle which will fit here. Okay, so this is the size of circle here, but the size of circle which fits here is bigger than the circle there. So that means the curvature of this is, so curvature, radius is bigger, radius of oscillating plane, sorry, oscillating circle at P is smaller than, so let's call this R of P, smaller than radius of oscillating circle Q. That means what? R of P is less than R of Q, but this implies 1 by R of P is bigger than 1 by R of Q. And these are what this is going implies 1 by R of P is essentially K at P is greater than K at Q. So the curvature at P is bigger than the curvature at Q. All right, so this takes care of the